Next topic is reflection and refraction. So we're going to try to understand the law of reflection. Define a few variables such as incident ray, reflected ray, the normal line, angle of reflection, angle of incidence, refraction, absorption, scattering, image, and object. I'm going to try to draw a ray diagram to show how virtual images are seen in mirrors. So how come I can see myself in the mirror when there's nothing behind the mirror? What does it seem like I'm coming from behind the mirror? We'll look at how we can create an image. We're going to draw ray diagrams for refraction and reflection, see the different properties of each, and understand how lenses work and draw ray diagrams for them. Going to try to understand how cameras take pictures and how the eye works. And look at how white light can actually be split into a spectrum by a prism, similar to what we saw at the start of this lesson. And finally, the colors of objects depends on what they reflect and what they absorb. For example, why is my jumper? No, my jumper is a bad example. But why is, for example, why do I see this slide here as being red? That's a big example because it's on the computer screen. But let's think of something else. For example, if I have a blue pillow, why do I see the blue pillow as being blue? That's because it absorbs all the light except blue light. It emits blue light, which is why I see it blue. So basically, what light objects reflect and absorb affects what the color we see them as. Okay, so wave properties, let's look at reflection. Waves reflect off some surfaces. For example, light reflects off mirrors. Water wave will reflect, water waves will reflect off a wall, for example. Sound waves will reflect off a wall as well. That's why we have echoes. So waves can be reflected, not just light waves, but probably most waves can be reflected. So what's the law of reflection? There should be reflection. It's law of reflection. So when a wave is reflected, the angle of incidence, so incidence is the incoming wave, measured to the normal, is equal to the angle of reflection, so the reflected ray. We've defined what the normal is before. The normal is an imaginary line at 90 degrees to the surface the wave is reflecting off. So in this case, if we have an incoming ray at a certain angle of incidence, the normal line is described as in this way. The normal is a line that's perpendicular to the surface. You can see a 90-degree angle here. And the angle of incidence is defined as the angle between the incident ray and the normal. That's the angle of incidence. Now, we know for the law of reflection that the angle of incidence is the same as the angle of reflection. So basically, A is equal to B. You have an incoming ray at an angle of A. The reflected ray will come out at the angle B, where A is equal to B. Note that we take the angle compared to the normal. We don't take the angle here. We always take the angle compared to the normal. Where, remember, the normal is an imaginary line that we draw just to visualize the situation and draw the ray diagram better. So imagine a line at 90 degrees to the surface, which we draw where the light ray touches the surface. So that's the law of reflection. Of course, this applies for a smooth surface that we can consider very flat with no irregularities. The incoming angle is the same as the outgoing angle. The incoming ray comes at an angle A, which is the same as the outgoing ray. Here the angle B is equal to A. That's the law of reflection. Okay, so for example, if we have an incoming angle, an angle of incidence of 45 degrees, then the angle of reflection will be 45 degrees as well. If I have an angle of incidence of 0 degrees, 0 degrees means it's perpendicular. It's 0 degrees, remember that we take the angle to the normal. So if it's 0 degrees to the normal, that means it's just parallel to the normal. Well, the angle of reflection will be 0 degrees. It will just be reflected perpendicularly like this. It's right back the way it came from. So that's a consequence of the law of reflection. The incoming angle, the angle of incidence, is the same as the angle of reflection. So if the angle of incidence was 60 degrees, for example here, the angle of reflection will be 60 degrees. So incoming angle is the same as outgoing angle. Oh, did I forget to add an image? Oh, that's annoying. Okay, just give me a second. Which letter shows the normal? Okay, wait, just a sec. There you go. Just gonna add the image now. Edit. Gotta add an image. There you go. So which letter shows a normal? Is it P, is it Q, is it R, or is it S? Sorry, I forgot to add the image. Hopefully that's not the case for the rest of the questions. Okay, so you've got a lamp, you've got a mirror, you've got an incoming ray here, and then a reflected ray here. Okay, what does normal mean? Normal in the case of geometry and physics means perpendicular to. For example, the normal force in physics is basically if I'm just standing, why am I not falling through the ground? That's because there's a normal force. It's the force of the floor on me. And this force is perpendicular to the ground. That's why we call it normal. That's why with it's basically used for perpendicular to. Okay, let's look at the answer. The answer is indeed R. R was so we can't really see in this, we can't really see the image here, but you can see R was the line that was perpendicular to the mirror. And that's what the normal means. It's the line that's perpendicular to the surface where the light ray is reflected. So the answer was indeed R. Okay, so that was the case for an ideal surface, a very smooth surface where all light rays obey the law of reflection. Now, what is scattering? Well, scattering is a type of reflection that happens on most surfaces. Basically, each ray of light obeys the law of reflection, but if the surface is rough, then each incident ray reflects with a different normal. It is known as diffuse reflection and does not produce an image. For example, you don't really see yourself. Okay, so here this is an ideal. Oh, my pen doesn't work. So this is the ideal case where you have a perfectly flat reflective surface and all incident rays reflect with the same angle. You can see they all come out parallel. They all come in parallel and they all come out parallel because they all have the same same angle of reflection. However, if you have a rough surface, for example, the surface of water or any surface in general, really? Well, because it's a rough surface, it's not perfectly flat, each light ray will touch the surface at a different point and at a different angle. For example, all the light rays here come in at the same angle. They all come in parallel. But depending on which point of the surface they touch, the normal will be different. For example, here, they touch, this light ray touches like somewhat flat part of the surface, but this one doesn't. This one is at a certain angle, and this one is at a downward angle. So they will be reflected at different angles. So they all obey the law of reflection, but because they touch the surface at different angles, because it's a rough surface rather than a flat surface, that's why we have what we call diffuse reflection. And they all come out at different angles. It's not a perfect reflected surface like here, where it's all very structured. They all come in at a certain angle and come out at another angle. In this case, because it's a rough surface, it's way more irregular, and it leads to very different reflected rays. So that's what we call diffuse reflection. So all surfaces reflect light. Basically, all surfaces reflect light. How do we know that all surfaces reflect light? Because we can see all surfaces. If I look outside and look at the car, why do I see the car? That's because light reflects of the car, reaches my eye, and I can see the car. Why do I see my computer? Because light is reflected of my computer and reaches my eye, which means that I can see my computer. Why can I see the wall? Well, because light from the sun reaches the wall, is reflected of the wall and reaches my eye, which means I can see the wall. So we know that all surfaces reflect light somewhat. Of course, some less than others. For example, a window doesn't reflect light as much as other surfaces, but they can. But we can say that all surfaces reflect light somewhat. However, we know that all surfaces reflect light, but only smooth surfaces, like mirrors, produce, is it a diagram, an image, a light ray, or an object? Remember the previous slide on diffuse reflection. What happens if I have diffuse reflection? That means that all light rays are emitted and all reflected in all different directions, which means that the light that comes in, is basically describes the object. For example, why can you see me as me? That's because light is reflected of me, and you can see it reaches your eye, and you can see me. Now, why can I not see myself on surfaces like a wall or something else? Well, that's because there's diffuse reflection. So only smooth surfaces like mirrors, which reflect most of the light, because you also need a surface that reflects most of the light, like mirrors. For example, sometimes I can see myself in the window because some light is reflected of windows. That's why I can see myself if my phone screen is turned off. I can see myself in the phone screen because light can be reflected of the phone screen. Can I go back to a previous slide? Yes, I can go back to a previous slide on diffuse reflection. So basically, in order to produce an image using reflection, you need a very smooth surface, such that the reflective surface can be considered really flat, and the law of reflection is the same everywhere. That's the first necessity. Second necessity is that the surface is highly reflective. If it's highly reflective, then you can produce an image. Because if most of the light is absorbed, then you just can't see anything. because it's just absorbed by the surface. Same, you can't produce an image if you have rough surface, because then you have light rays being reflected in all directions, and that just all the information that was in the incoming light rays is lost because it loses all this structure. So that's why you can't see yourself. Okay, so let's talk about mirrors. A mirror is a flat reflective surface. Reflections from a smooth surface is called specular reflection. So we saw before diffuse reflection when it goes in all directions, but when it's from a smooth surface, it's called specular reflection. It also happens in water and glass. Water less so because it can be quite rough, but glass definitely because it's a smooth surface. So basically, imagine I have an object and I have a mirror, and I'm looking at the mirror like this. Light reflects off the object onto the mirror. So, for example, light from the sun goes on the object and is reflected towards the mirror. So you've got light from the object going towards the mirror, represented with the light rays here, with the arrows. It reaches the mirror, and then when it reaches the mirror, it of course obeys the law of reflection. So if you draw the normal, the angle of reflection is the same as the angle of incidence for both rays. The light reflects off the mirror into your eye. So basically it's reflected and then reaches your eye. How does it then produce an image? Well, your brain knows light travels in straight lines and sees an image of the object in the mirror. Basically, we know that light travels in straight line. So light coming in this way is basically, it seems like it's coming from behind the wall. It seems like it's coming from behind here. It's as if this image was emitting light rays, which fit what we see here, being reflected of the mirror. So that's why we can see images behind mirrors, because it's when the incident light rays are reflected, then it looks like the object is emitting from behind the mirror and producing this image here. That's why we see in this case, the apple behind the mirror, because it looks like it's coming from behind the mirror. However, it's not a real object, it's an image of the object in the mirror. And that's all thanks to specular reflection, because imagine if this was a rough surface. Imagine if this wasn't just a perfect reflection coming in and coming out. Then we wouldn't be able to see this image because it would be an irregular. For example, this one could be reflected behind here, and this one could be reflected here, and we wouldn't be able to reproduce a clear image of the object. So we need a very smooth surface, we need specular reflection. So an image is basically an optical or representation of a real object. For example, a photograph, a reflection, or a projection. An object is the original real thing the image is of. For example, here, the real object emits light on the mirror, which is reflected to our eye, and it looks like the image is coming from, it looks like the light is coming from behind the mirror, and this is from the image. It's basically a reflection in this case. There are two types of images. You can have virtual images, so reflections. This is a virtual image. Or you can have real images, such as projections. So a virtual image is caused, as it says here, is caused by reflections, and a real image is caused by projections. Okay, so practice question 6a. Which point, A, B, or C, shows the position of the image of his hat? Is it A, is it B, or is it C? So basically, the top of the hat is emits some a light ray. The light ray is reflected off the surface, here the mirror, and then reaches his eye. what is the position of the image? So remember here we consider the position of the image, not of the object, but of the image. So the image, as we said before, in this case is a virtual image. It's caused by reflections, and it's basically where the light rays seem like they're coming from. Okay, 5-10 more seconds, and then we look at the answer. Okay. It is indeed answer C, point C. Because if you look back at the image here, so the light ray comes in, and is reflected of the plane of the mirror at point B. When it's reflected, it obeys the law of reflection, of specular reflection, and it's reflected back to our eye. So when we see this light ray, where does it look like it's coming from? Well, it looks like it's coming from point C. Of course, this is we would need to draw more than just one light ray to show that it's coming from point C, but it looks like it's coming from point C. If you draw more than one, for example, one coming from the middle of the hat, it would be reflected of here just below point C, point B maybe, and reach our eye, and it would look like it's coming from around point C as well. This is more, you can picture this more if you have more than one light ray, but in general, when you have a plane mirror, it's basically symmetrical. Whatever you have here is symmetrical on the other side. So it will be at an equal distance. It will seem like it's coming from an equal distance, and it's just basically just a reflection like a butterfly, for example, that it can close on itself. So the image will be at point C. It's where the image of the hat is, because it's where the light ray seems like it's coming from. It's not on the plane, it's not answer B because it's not on the mirror. It seems like it's coming from behind the mirror. Okay. On the diagram, use a ruler to draw a light ray to show how the person can see his shoe. So how can the person see his shoe? The shoe is here. The shoe will not emit light, but light will be reflected of the shoe in all directions, and it will basically emit light in all directions. If it emits light in this direction, it's reflected here of the surface and reaches our eye. This is the only way light from the shoe can reach our eye. It's being reflected here, like halfway between our eye and our shoe, touches the plane mirror, and is being reflected back to our eye. So basically, okay, point of reflection should be within these limits. The shoe emits light, is reflected of the surface, and then reaches our eye. Similar, like we had with the hat. Hat emits a ray of light, reflected of the mirror, and reaches our eye. And then, with these reflected rays, you will see that it seems like the shoe is coming from here, under point C. That makes sense because it's all, remember, it's all symmetrical. Okay, practice question 6C. What type of image is produced by a mirror? Is it imaginary, is it real, or is it virtual? Okay, imaginary, real, or virtual. Remember, we've introduced two of these. One of them hasn't been introduced yet, but we've said that one can be produced by reflections and the other ones can be produced by projections. If it's a mirror, it's a reflection. So what type of image will it produce? Imaginary, real, or virtual? Okay, 5 more seconds. It is indeed virtual. Virtual images are produced by reflection. Real images are produced by projections, which we'll see later on. So far we've only seen virtual images, which are produced by reflection. A mirror produces reflections, so it's a virtual image. Okay, so it's virtual. Now, let's start talking about refraction. So we've talked about reflection, where there's a simple law of reflection, where the angle of incidence is the same as the angle of reflection of the surface if we have specular reflection. And we've looked at this difference between specular reflection and diffuse reflection. So light wave can carry on traveling through a transparent or translucent material. We've talked about transparent and translucent material, is where basically if it reaches a boundary to transparent or translucent material, some of it will still go through the boundary, so not be reflected or absorbed through the surface. Some of it would just carry on through the boundary. As you can see here, the incident ray has a certain direction. When it reaches the boundary of a transparent or translucent material, it's slightly refracted. It slightly changes direction. So that when the light waves travels into new material with a different density, that's the important point to note here, is that we are considering with a different density. Its speed changes. Obviously, if the density of a medium changes, then the speed of light will change, because it's basically there will be, if the density increases, you can imagine there's so much more stuff in the way of light propagating, so the speed will decrease. And this will cause the wave direction to change. So this is to explain why the direction changes. It's a bit more tricky. You should just know that if there's a change in speed, there will be a change in direction for light. So basically, light comes in. It has a certain initial speed in the incident ray. It reaches the boundary to a new medium. This new medium has a new density, so the speed changes, so the direction of light changes, and we have a refracted ray. This is called refraction. And refraction happens to all types of waves. So basically what happens? Light travels faster in air than in gas. Let me just take back there you go. Light travels faster in air than in gas. Sorry, in glass, my bad. So what we have here is a little diagram of what a light looks like when it goes from air to glass. Here we considered just an easy example, 90 degrees to the boundary, so just an incident ray perpendicular to the boundary. So we have the ray diagram here. We can see the direction of the light, and we go from long wavelengths in air to shorter wavelengths in glass. Okay, so why is that the case? Basically, in refraction, you should know that the frequency of the wave is conserved. That's a very important, I wish, not right for example, for some reason, but the frequency of the light is conserved. So the frequency before of the light is the same as the frequency after. But this time the speed changes. We go from a high speed in air to a lower speed in glass. So if we have a frequency that stays constant, but we decrease in speed. If you remember your wave speed equation, V is equal to wavelength times frequency. If the frequency is constant, let's ignore it. Let's just say V is equal to frequency. So, sorry, V is equal to wavelength. So if the speed decreases, we know that the wavelength will also decrease. So basically what happens is we go from the first substance, air, where we have a high speed and a certain wavelength. We go to substance 2, glass, where basically the speed changes. Because the density changed, the speed will change, the speed decreases. Because the speed decreases, and we know that the frequency is constant, then the wavelength will decrease as well. So basically, light travels faster in air than in glass, so the wavelength will decrease when it will go into glass. However, at 0 degree angle, there's no change in direction, it just goes straight ahead. There's no, because we have 90 degrees to the boundary, in this case we don't see any refraction, we don't see any change in direction. That's the special case of 90 degrees to the boundary. So an angle of incidence of 0 degrees to the normal. So now let's consider a more tricky example where we have an angle of incidence that's non-zero. So we have a certain angle to the boundary. So light travels faster in air than in glass. So that's why we see that the wavelength increases when we go into a when we go from glass to air. We have an initial wavelength that's quite small, and then it increases because suddenly it goes faster. Remember your equation, speed is wavelength times frequency. Frequency is constant when we go from one substance to another. So we have basically speed is equal to wavelength. So if the speed increases, that means that the wavelength will increase. Going from one medium to another, if the speed increases, the wavelength will increase. If going from one medium to another, the speed decreases, such like we had before, then the wavelength will decrease as well. So at any non-zero angle, there's a change in direction. You can see here we have a certain angle of incidence that's non-zero. There will be a change in direction. Ray bends towards the normal. Okay, so that's not the case here. I don't know why it's written ray bends towards the normal. In this case, that's not the case. So ignore this for now. Basically, if we draw the normal here. Okay, sorry, I need to write with my mouse, which isn't the easiest thing. We go from a small angle of incidence to a bigger angle, refracted angle. So we have I here, the angle of incidence, and R, the refracted angle. If we go into a quicker medium, so a medium where light goes quicker, then the angle will increase. So if speed increases, the angle will increase. If speed decreases, the angle will decrease. So let's do an example where the speed decreases. For example, here, let's consider we have water. Let me type water. Okay, we have an incident ray at a certain angle of incidence I, and we have a refracted ray at an angle of incidence R. You can see that in this case, the ray bends towards the normal. So why is that the case? Here we go from air to water. So air, we know that the speed of light in air is bigger than the speed of light in water. So if the if the speed decreases, going from air to water, then the angle will decrease and it will bend towards the normal. What is the angle of incidence again? Angle of incidence is the angle between the incoming ray of light, so this ray of light here, and the normal. Remember, the normal is an imaginary line that's perpendicular to the boundary. So you have the boundary here, that's vertical, and the normal is horizontal, is perpendicular to the boundary. So this is your angle of incidence here, I. If you go from a medium where going from quicker to slower, if the speed decreases, going from air to water, the speed decreases, so the angle will decrease. So that's how you can kind of think of how the angle changes. We saw before that if we go from glass to air, in this case, the speed increases. In this case, v, the speed increases. Light is quicker in air than it is in glass. So if the speed increases, we know that the angle will increase. That's why we have a big refracted angle. Now, in this case, we go from air to water. So initially we have a high speed and we go in the medium with a lower speed. So in this case, speed decreases, which is why the angle will decrease. The angle of incidence is bigger than the refracted angle. So here, ignore, it's the wrong way again, so ignore this. So here again, we go from air to glass. There's a certain wavelength initially. Then suddenly, when we go from air to glass, the speed decreases. If the speed decreases, the wavelength will decrease and the angle to the normal will decrease as well. Oh, my bad. The angle to the normal will decrease as well. So that's why initially you have quite a big angle to the normal, and then we have a smaller angle to the normal. So it's all linked to speed, really. If speed decreases, wavelength will decrease, and the angle will decrease. Remember, the angle is always taken when compared to the normal. Okay, so in this example, we see it better. Let me take back my... There you go. We have an initial angle of incidence I, where here we go from a medium, let's consider like this is glass and this is air. When you go from here to here, the speed increases. If the speed increases, the angle to the normal will increase as well. As you can see here, R is bigger than I. R is bigger than I. So if speed increases, the wavelength will increase and the refracted angle will be bigger than the angle of incidence. So it's all linked to speed. If speed increases, wavelength increases, angle increases. If speed decreases, wavelength decreases and the angle decreases. So it's all linked to speed, and speed is linked to density. If the density increases, then speed decreases. So there's this inverse relation between density and speed. Imagine if the density, if a medium is really dense. For example, if I'm trying to walk through a crowd with many, many people, it's a very dense crowd, then I won't be able to go forward really quickly. So if the density is really high, it will be quite slow. However, if I've got no one in front of me, if I just have one or two people, then it's a very low density, there's not that many people, but I'll be able to go much quicker. So basically, the bigger the density, the lower the speed. The smaller the density, the bigger the speed. Okay, a ray of light meets a boundary, the new material is more dense. Does the ray refract towards or away from the normal? Okay, so this is, you really need to think of the chain reaction. So if the new material is more dense means you increase the density. What happens when you increase the density? If I increase the density, that means that there's more stuff in the way, there's more stuff obstructing the propagation of light, which means that the speed will decrease. If you go into a medium that's more dense, the speed will decrease. There's a decrease in speed when you go into a more dense medium. Now, what happens if the speed decreases? I said that it's all linked to speed. What happens when speed decreases? I said that when speed decreases, you've got the wavelength that decreases. And what happens to the angle? I said before that it's all linked to speed. So what do I mean by refracts towards the normal or refracts away from the normal? If a ray refracts towards the normal, that means that a refracted ray gets closer to the normal. If it gets closer to the normal, that means that the refracted angle is smaller than the angle of incidence. If it gets refracted away from the normal, that means that the refracted angle is bigger than the angle of incidence. It gets away from this perpendicular line. Okay, so think again, it's all linked to speed. We know that we go into a medium that's more dense. If you go into a medium that's more dense, that means that we go into a medium that's slower. So we know that the speed decreases. If the speed decreases, I said it's all linked to speed. If the speed decreases, we know that the angle will decrease. So what does that mean if the angle decreases? Does that mean that the ray gets closer to the normal or gets away from the normal? Just go wait maybe for 5 more seconds if there's any more answers. That's quite a tricky question because obviously you really need to think in your head. It's kind of like a thought experiment of what happens in each case. Okay, let's look at the answer. So it's quite split between the two, and the answer is indeed the ray refracts towards the normal. So if the density increases, the speed decreases. We know that if the speed decreases, we know the angle also decreases. If the angle decreases, that means that we get closer to the normal. The ray refracts towards the normal. So let's look at an example we had before. This one here. So this is exactly the example we have. We go from air to glass. So we go into a more dense medium. As we go into a more dense medium, we know that speed decreases. As I said before, if speed decreases, that means that let me go back to this. If speed decreases when going into a more dense medium, we know that the angle decreases. It's all linked to speed. So we have speed decreasing. So the refracted angle is smaller than the angle of incidence. As you can see here, the angle of incidence is bigger than the refracted angle. Remember, that's all compared to the normal. The normal is this perpendicular line here. Now, if the refracted angle is smaller than the angle of incidence, that means that the refracted ray got closer to this normal. If the angle is smaller, that means that it got closer naturally. So basically, when you go into a more dense medium, the refracted ray refracts towards the normal. Okay, well done to 3 people that still have 15 out of 15. Okay, practice question 7. The diagram shows a ray of light traveling through a glass block. So you've got glass and going into air, and you've got the normal here perpendicular to the boundary. Complete the diagram to show what happens to the ray of light when it comes out of the glass. So we go into a more dense medium, from a more dense medium to a less dense medium. That means that going from glass to air, what happens to speed? Speed increases. Speed increases when going from glass to air. If the speed increases, we know that the angle increases as well. So we have an initial angle of incidence of I. If the angle increases, that means that the refracted angle is big. Let's draw it like this. There you go. Is bigger than the angle of incidence. It gets refracted away from the normal. So what does it mean when I say it refracts towards the normal? So you can see from before, it's basically if you think of the direction of the rays. If you think of the incident ray having a certain angle like this, okay, the previous image is better probably. It has a certain incident angle like this. What I mean by it gets refracted towards the normal is I mean it gets basically this, it gets closer to the normal. That's what I mean. How does it move towards the normal line? It's basically the angle gets closer to the normal line. You see this angle here has quite a big angle to the boundary. And then when it gets refracted closer to the normal line. That's what I mean when I say it refracts towards the normal. It's basically initially we have a certain angle, and then when it's refracted, it gets closer, it gets deflected closer to the normal line. That's what I mean when I say it gets refracted towards the normal. So in the opposite case, where the speed increases, it gets refracted away from the normal. You can see that the angle increases, so it gets refracted away from it. Explain why this happens to a ray of light. Well, that's because speed increases. So ray is refracted away from the normal. That's because it travels at a different speed and it travels more quickly in air. Okay, let's do this last slide, and then it will be the lunch break. So in reality, when light enters a new medium, some of the light is reflected, some is absorbed, and some travels through. You've got everything at the same time. You can see this in windows, for example. Most of the light travels straight through the window, but some of the light is also reflected, and some of the light is also absorbed. So that's something we'll see after the lunch break. So it's now 12:30. So let's have the lunch break now, and I'll see you guys in 45 minutes. If you have any questions, don't hesitate to use the Q&A. Something you haven't understood, and I can answer by chat. So lunch break until 1:15. I'll put that in the published chat. Lunch break until 1:15. Okay, have a good lunch break, everyone, and we'll carry on the lesson in 45 minutes. Okay, I'll see you in a bit.